I dug out this project to resurrect. Here we go. This is the way I left it. I started accumulating some pieces. Cream cheese clock. IV-11 VFD tubes. And I had a pretty good head start on this. So this board, the display board, is ready to rock and roll. The power supply, I have to refresh my memory. I think I did something unique with a center tap transformer to get 2 DC supplies out of it. And then the filament circuit, isolated AC. This is a horribly dark schematic, but this is the Archer kit clock that I've worked on in the past. This is right out of their manual. I'm going to pretty much copy this schematic for the build. Yeah, it looks like I have some notes here. That's good. Write it down. If you're building something, write it down. It's great if you ever have a problem to go back to some of your notes. Comes in very handy. It's the first time I've ever tried this. We're going to see how this works. Center tap transformer with 2 capacitors to split the DC output, which should work as long as the loads are similar, I guess. It looks like I began to do the pinout. I typically, for perfboarding, do the pinout upside down. I have to complete that yet. That way I don't have to keep flipping the board over to see what I'm doing. So basically I draw it all backwards and then build it. So that I have to continue. Alright, we're into the project a little bit. It's been a while since I've sat over the bench. We got this green perfboard. And this is the first time I worked with this. It's tough because these silver pads here really got a lot of glare on them. So I took the Scotch-Brite I have handy here, and before I started populating this with components, I scuffed it up a little bit, and it's quite a bit better, but still a little tough to work on. And you know, the eyes aren't the same. I tried working with one of those hood magnifiers, and I don't like those things. So you got a couple pairs of cheaters, stack them up. It works good. You can put 2, 3 on, whatever it takes. So we're getting into this. Transistors I had on hand here are NPNs. That's what the circuit's going to take. And starting to put things in. Flipping back and forth. The display board here sized up. It'll be a double decker with standoffs screwed together. And this cream cheese box, I'm starting to think if this comes out nice looking, maybe I'll do a clear enclosure. I don't know. We'll see. These things sometimes develop as you build. So we have most of the circuit built up, including the DC power supplies. We got 2 voltages here to check. I always like to check before connecting it to the circuit. So currently the supply has just been fired up and is not connected in circuit. So it's unloaded, and we're looking at 18 volts and 36.2 volts. Okay, so the 18 volts is a little high. Might massage that a little bit through a couple diodes. It's very close to the max rating of the clock IC we're using, So we can knock that down a little bit and massage that down to maybe closer to 16 volts. Other than that, we're looking pretty good. And then we have on a separate transformer, yes, we are running two transformers because I couldn't find the transformer I wanted. So we opted for a second one because we need an isolated filament supply, and AC is best with vacuum fluorescent displays, and it's a 9-volt transformer unloaded, putting out 12.2 volts. The excitement is on. We're getting near the end of the build here. The anticipation is overwhelming. So you've been following along my channel. You know, one thing I never talked about too much was what dictates the size of the build as far as Perfboard and what have you, the overall size in the end. Well, I guess just starting with whatever display unit you're using, in this case the IV11 vacuum fluorescent display tube, and considerations from there are they socketed? Do they have wire leads? The electrical characteristics, driving circuit, power supply, that sort of thing. Also, proportions. Now, these IV11s have a proportion that led me to build something about this size, but the other thing you have to consider is what kind of case you're going to use. So just kind of running things through the head here, I came up with one of these my mother had laying around, and I built one other out of a cheese box like this, and it's kind of very handy. So proportions, that's not too bad, right? So I got the Perfboard cut to fit, and I knew I was going to have some pretty tall transformers, at least one, but we ended up with two because of the circuit design here and not being able to find an all-inclusive transformer. So we're going with a double-decker construction, right? And use the standoffs in between. We'll go with 6, 3 on each side for pretty good support. That's a little bit about what goes into it, and then from there just placement in your established real estate. And this case we kept the circuitry off to one side, and I kind of knew about where these two transformers were going to live and built off from there. Structure, you know, consider the weight of the transformers. I got a couple extra standoffs so the board doesn't flex. You know, things like that. This is the clock circuit schematic that we're going to use. It's based on the Archer kit clock I've featured in the past. It's a 1 year only clock, 1974. But this circuit was appealing to me because it's pretty straightforward, and again, it's going to use my favorite MM5314. I'm the only one of probably a couple still building clocks in 2024 with this IC. Long defunct, obscure, and getting harder to find. So this circuit drives 6 vacuum fluorescent display tubes, and here we have those represented here. 1, 2, 3, 4, 5, 6. The filaments are strung out in series through all 6. And the filaments like an AC source. The tubes illuminate better on an AC filament driving source. They will work on DC as well, but this clock will show a separate supply just dedicated for the filaments alone. Okay, just so we can landmark, you have 6 transistors to drive the grids of the tubes, and up here we have a pair of transistors times 7 for the 7 segments in these tubes. A little bit of how these work, we'll just focus on the A segment here. Okay, with you got Q7 and Q8, and keeping in mind that on our segment outputs a high condition is active, so when we want to activate a segment, the output of a particular segment, and we're going to focus on pin 3 here, will go high. Alright, in order to illuminate a segment on your output, which is at the top of Q8, alright, this transistor has to turn off. Alright, what we have here is our 40-volt rail to the segment transistor, and through a 15K resistor to the top of Q8 here, and then on the emitter side of that transistor we have our ground bus all the way across. Alright, so with this transistor off, through our 15K resistor here, this line will be high. Alright, we'll have a potential on it, thus lighting our segment. When Q8 turns on, alright, now you have a straight path to ground. Your output over here will be low, turning the segment off. This transistor here basically inverts, it controls QA here. Alright, and it works in the same manner. Alright, so we apply a high signal to the base of Q7, alright, and that'll turn it on. What that does is now sends this path straight to ground. The base of Q8 goes low, thus turning that output high because this transistor opens up. That's pretty much how that works in a nutshell. Takes me a little bit to wrap my head around it each time. I'm not a circuit designer, and I can marginally work my way through how these transistors act together as a pair. Down here, alright, the digit enable. That means each tube, 1, 2, 3, 4, 5, 6, is controlled with its own line here, its own transistor. We only have one transistor to look at, and when an active condition low on your output, okay, that turns this transistor off, alright, opens this up, and that puts a high potential at the grid through this 10K resistor. Alright, the minute this goes back high in a non-active output, this transistor turns on, bringing the emitter again to ground, and your potential goes away at the end of the 10K resistor. Power supplies. AC supply just for the filament, isolated. Okay, 12 volt AC, filtered, rectified, that goes up to 1414 plus. That drives the module. It also provides some biasing for the transistor rail up here. And we have a 30 volt winding. Alright, filtered, rectified, and you end up with almost 40 volts on that rail. 40 volts is high, very high for a vacuum fluorescent display tube, but in a multiplex or a pulsed scenario, that is typical. Finding a transformer for this project was an issue. I did try and scour the internet a little bit. I needed something small, something with multiple outputs, especially with a separate filament winding, which would be isolated from the rest of the circuit. That was hard to do, and that's pretty much why I went with two transformers. We have a center tapped 12 plus 12, so it's a 24 volt, but center tapped winding on this one. This one is a 9 volt rated output, center tapped. We don't need the center tap, but we're going to go across the two ends for the 9 volts, and this one will be dedicated just for the filament string. This is our row of segment driving transistors, and this is our row of digit driver transistors. The MM5314 will nestle in this socket, and I also set up some header connectors here, so when I put the display board on top, it'll be easy plug-in and easy service. So we have 7 pins here. That'll be for one each of the 7 segments. This one, there's 6 pins. That'll be one each for each of the tubes. Over here we have a 4-pin connector, and that one will be ground and then slow, hold, and fast setting. As we're not quite done with this project yet, we have to do something on this side to be able to connect the filament string up on the display board. That has yet to be done. We are getting close to getting this fired up. The anticipation's high. So this side filament plus a reference. So as I said before, the filament string is going to be isolated, but it does have to be referenced to ground. Without the reference to ground, there will be nothing to complete the circuit for the tube to work properly. The reference to ground was going to be through a resistor, and in this circuit here we have 2 different resistances that reference to the ground bus here. Okay, so using 2 different resistors, you can actually control brightness. Alright, so we have a 10K and a 1.5K. I'm going to verify that those are adequate for me. I don't know if I'm going to put brightness control in this. I may just find a resistance in the middle. I'll use a resistance substitution box probably once this thing's fired up, and just dial in the illumination I'm looking for, and then settle at that resistance. Without the reference to ground on the filament string, there'll be no relationship between the filament and the grid and or segments. You need an active filament to stimulate electrons, and a grid powered high to attract the electrons, and a segment powered high, or segments powered high, to attract the electrons, thus illuminate the phosphor. So without that reference to ground, you don't have a complete circuit. So I said AC on the filaments, and that gives each segment a nice uniform glow, typically, from what I've been reading. If you don't have that reference, that process is not going to happen. Okay, a little pre-power up check. Stage 1 here. Being that this project started over a year ago, I'm at the point where I want to check my filament limiting resistance. So here's my string of filaments, like a string of Christmas lights, and 9 volt AC, but with minimal load. We're 12 volts, so we just got to take that into effect. each one of these tubes is a 1.5 volt filament. String those up, that's 9 volts. But with the unloaded or low loaded winding here, they kind of float up on a higher voltage near 12. So what we'll do is, I think I figured this out sometime back. I had a 3/8 watt 51 ohm resistor figured out. I guess I either tested it or calculated it. I don't remember. But coming back into it, I'm figuring since I have 51 written down, let's start up at 150 ohms, hook up a meter, and measure our FIL I have here. And those tubes also are rated for 100 milliamps a piece. Strung in series, it should still be 100 milliamps. Okay, so that's what we're going to check now. I'll flick on the power here. I have a kind of a nasty suicide cord hooked up to the transformers, and a resistance substitution box with a meter. Everything's all hooked up other than one lead. I'm going to insert that now. And look at that. Okay, 45 milliamps AC, and we're good up to 100. Okay, so the IV11 filament 1.5 volt to 100 milliamps. Alright, so let's dial down. We're at 220 ohms. 150 ohms. Okay, that's 100 ohms, 66 milliamps. 68 ohms, 78 milliamps. And 47 ohms, 87.5 milliamps. Okay, so that's, I have written down here, I must have done this before, so that 47 ohm resistor in that box actually measures 51 ohms, and I have written down 86 milliamps. I apparently measured across each tube too, 1.1 volt each tube. So we're going to shoot for 50 ohms, maybe 2 half-watt resistors in parallel, so maybe if we can find a pair of 100s. And I think I settled in. We'll keep it under the rated 100 milliamps, run things a little less off of peak values, and no smoke, no filaments glowing. So I think we're in good shape. It's a good double check. So in this clock circuit, when we speak about multiplexing, basically these tubes are scanned one at a time to display a display faster than the eye can see. And the advantage to that is the wiring is way more simple, less conductors are needed, and it really saves on construction time. So this video is getting pretty long at 25 minutes. We're going to end it here. Keep an eye out for part 2 where we fire this thing up. Thanks for watching.